a magnetic field. The detector changes that current rapidly, so the field is not sitting still. It expands, collapses, and changes direction. That changing field reaches into the ground, not very far, but far enough to disturb certain buried objects. A simple magnet can attract iron, but a metal detector needs something more subtle. It uses a changing magnetic field because changing fields can induce electric currents in conductive metal. That means a buried coin does not have to be magnetic to be noticed. Copper, silver, gold, aluminum, and brass can all respond because their electrons can move. The detector is not only asking, is this magnetic? It is asking, can this object carry a current? When the detector's changing field crosses a metal object, electrons inside the object begin to circulate. These loops of current are called eddy currents. They are small, but they matter. A buried coin briefly becomes an electrical object with its own magnetic field. That field is weaker than the detector's transmitted field, but it reaches back to the coil. The buried metal has answered. Inside the detector, electronics separate the signal being transmitted from the signal coming back. Some designs use one coil to transmit and receive. Others use separate coil windings. Either way, the machine is looking for a slight change. The received signal may be delayed, shifted, stronger, weaker, or shaped differently depending on the object. The return signal is buried inside the detector's own stronger field, so the electronics have to subtract, compare, and filter quickly. A good detector turns that tiny electrical clue into a sound, number, or visual target ID. One of the most useful clues is phase shift. The detector sends a signal with a known rhythm. The target's response comes back slightly out of step. Conductive metals, rusty iron, thin foil, and coins do not all shift the signal in the same way. Iron often pulls the response one way because it